Hello, everyone. Oh, hello. So welcome to the first series of capstone presentations by Astronomy and Space Physics students. I'm really excited to this talk. So for this talk, we have 9 students presenting today, and the presentation is being live streamed for anybody to watch. So we're gonna try to use the mic as much as possible, especially when you're asking questions. Raise your hand and we'll get the mic to you, so that when you are recording it, it becomes audible. Anyways, so with that, we have Thomas Zanin presenting first. Each talk is gonna last for 5 minutes, so I'm gonna have a stopwatch right here for you all to see. You can get a reference there, and then immediately after the end of each talk, there's 1 minute dedicated for questions. Okay, so 5 plus 1, 6, and we have nine students, and 1 is a combined talk. So we'll make it through in an hour. So first presentation is by Thomas Zanin, who's going to be talking about quantum discord of gravitation detection entanglement. All yours.
Hi guys. Is this okay? Can everyone hear me? I've been a little sick, so sorry about that. I'll do my thank yous and everything at the end. So we're going to talk a little bit today about quantum discord, like Pradhan said, and I'm Thomas. So I'm going to stand back a little bit. First, we got to define discord. So it's just the difference between the total mutual information and the classical mutual information. So what that means is you're talking about the distance between the classical regime and the quantum regime. And the nice thing about discord is that it captures correlations that might be missed by entanglement. So that's kind of why it's so interesting. So entropy in the quantum context. Here we're looking at the standard Shannon entropy, von Neumann entropy. And this is Rényi entropy of order 1. So it's kind of how mixed a state is. Here is kind of where my research began. So we looked at these quadratures. Here's a phase space diagram down here that I made. So you can think of these quadratures as defining a geometry that goes with the uncertainty in the phase and the amplitude of a light wave. Now we want to talk a little bit about sub-Poissonian statistics. So here your mean is just less than your standard deviation, and that's why it's called squeezing, because this wave is narrowed here. This is the probability distribution. So these sub-Poissonian statistics are a completely quantum phenomena. We don't get them classically, so this is a good indicator that your system is quantum. So some motivations. Here's the smoking gun that we always talk about. I didn't think a gun would be a good choice, so we did a finger gun instead. So if we find squeezed gravitational waves, we'll see sub-Poissonian statistics, and then we know gravity is quantized, and we all go home. There's no more problems to do. We win. But we're going to see some problems with that. Quick assumption before I go into a little bit of a calculation for this quick talk. We're assuming one polarization, which is a logical assumption. LIGO often can't tell the difference between the two polarizations. So these are the plus and cross polarizations. You'll kind of see them squeezing in GIFs often, but I couldn't really figure out GIFs. So we'll get into the covariance matrix development here. Here's our squeeze operator up here, and this guy R is the important part. Here's our squeezing parameters. And then A and B are our creation and annihilation operators for the two modes. We can use our quadratures to create our covariance matrix. Now we can use block decomposition to find our subsystems here. I'm going to go through this a little quick. And then we can use symplectic eigenvalues to find the characterization of these two subsystems. And then there's a known formula. We plug this in, and we can calculate the discord. Now, I said it was the difference between the mutual and the classical information, but we're going to see that one of those falls out because we're talking about a two-mode Gaussian state. So, sorry about that. So just like I was saying, the global entropy vanishes, and we're just left with this. That's it written out when we plug it into the function. Now, let's talk about some problems. So the generation of these states is highly unlikely. The current running candidate in the theory is axion inflation. We don't even know if that's true, so we're taking one step away from reality there. And then if we accept that's true, the odds of producing these squeeze states from axion inflation are also incredibly low. So things are not looking good. The motivation was super good, but now we're kind of worried that they don't even exist. The other thing, community opinion. These waves would be outside LIGO's current sensitivity bucket, which is maxed out at about 10 kilohertz, and we would be outside of that. So we would have to convince a whole bunch of people that love looking at black holes that maybe there's something else we should look at, which is a hard job. And then I don't have the slide on here because I sent these in a while ago, but there's lots of applications for Discord other than this hyper-specific scenario. Lots of quantum cryptography applications. I'm going to be doing a project in my cryptography class about quantum key distribution. So I can send those around when I'm done with that project if anyone's interested. The other thing is optimizing injected squeeze states into the LIGO lasers. You LIGO people use squeeze states all the time, and quantum Discord can be used to optimize those. And yep, perfect. Okay, questions? Oh, and thank you to Dr. Jones and Dr. Poon and Dr. Bailey and all my friends for keeping me alive. Anything at all, don't take it easy on me. Okay, cool. Ryan is going to follow me. Let's give a hand to him.
Well, my talk's already there. I'm trying to see how good it is.
Oh,
yeah.
The bottom right.
Where's the... hello. So I'm Ryan Topman, and I'm going to be talking about some of Voyager's detections that's been getting in a close interstellar medium and the potential correlation with gravitational waves produced by neutron star glitches. Now, since August of 2012, Voyager has crossed the close interstellar medium, or crossed the heliopause into the close interstellar medium, and its plasma oscillation detector has detected multiple plasma oscillation events, as can be seen here, 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 and so forth and so on. Now, these events happen between the 1.9 to 3.5 kilohertz range, and we also have a 2.5 kilohertz cutoff threshold for the measurements themselves. As also can be seen, most of these events are correlated with cosmic ray detections, as can be seen here, here, and throughout the rest. Now, as you get into the later detections here and here, we're approaching the cutoff frequency for the plasma density within the close interstellar medium. Now, the detection of both cosmic rays and these plasma oscillation events could motivate them being from neutron stars, specifically neutron star glitches. Now, neutron star glitches themselves tend to produce gravitational waves, not electromagnetic radiation, like what's interacting with the plasma. Now, to correlate this, we have to consider co-production. Now, what is co-production? On a simple sense, it's the interaction between gravitational radiation and electromagnetic radiation. First theorized by Faraday, as can be seen here by this diagram, which was his experiment trying to measure the electromagnetic induction from gravitational waves and gravitational fields. Now, of course, it's gotten more modern over time. Currently, we're working with this here, where you set your electromagnetic intensity equal to your strain amplitude and your gravitational intensity. Here you can see the actual equations that go with your gravitational intensity and your strain amplitude. Now once you plug those in and you solve with some simple assumptions, such as the radius of your neutron star being somewhere in 10 to the 4th meters, it spits out this here for your electromagnetic intensity on the order of 10 to the negative 85th as a function of your luminosity in watts and the distance from your source r. Now, sadly, once you get to the plasma in the close interstellar medium, you have to add a unitless coefficient of efficiency between the electromagnetic radiation and the what Voyager's detecting with the plasma oscillations itself. Now, taking the maximum intensity here that Voyager has been detecting, you're able to find the electric field strength, symbolized by E here, as a function of your luminosity and your radius, or distance from your source, sorry. And from that, what you're able to do is start to visualize the data. Here we can see our distance from our source here, the luminosity of the source, or the neutron star glitch, and the energy here. Now, all this is log-based, so that way it gives a better correlation of the data, with the lighter gray being the electromagnetic field itself, and the darker gray area being the actual range that Voyager is detecting from 2 to the negative 5th to 2 to the negative 6th voltmeters. Now, obviously, how did we come across an assumption of our efficiency being around 10 to the negative 6 here? To do that, we moved this equation around a little, so that way we could set our distance here as a function of our coefficient of efficiency, assuming with the blue line being the maximum these neutron star glitches could produce, and the minimum being what these neutron star glitches could produce. The area in between is all potential ranges for these events. Now, we chose 10 to the negative 6th here simply because we assumed our closest neutron star source that's known, which is about 100 parsecs away. So 10 to the negative 6 sits right about in the center there of what we'd expect given that assumption. Now, in a perfect world where we'd have perfect efficiency, we could be detecting things all the way up to 150 megaparsecs away. Sadly, though, this is not currently in LIGO's bin to be able to detect, so they'd have to move this. But because of the assumption of co-production, they'd be able to validate these results by detecting gravitational waves that come along too, to co-production and correlate them to Voyager's detection themselves. Thank you. Questions?
Hi, great talk. Just a quick question. Why are neutron star glitches better to look at as sources of this rather than binary black hole end spirals?
That's actually a great question. I'm not sure on that answer. I'll have to talk to Dr. Jones and get back to you on that, because that is a very good question. Thank you. Speaking of, I'd also like to thank Dr. Jones for giving me this opportunity to do research. Yep.
Hi everyone, my name is Jasmine Downing, and today I'll be talking about a spectroscopic orbit for WR70. Before I begin, I would like to thank Dr. Noel Richardson for all of his support throughout this project. So what are Wolf-Rayet stars? Wolf-Rayet stars are stars in the late stages of evolution that have lost their outer hydrogen shell and are now fusing helium or other heavier elements in their core. These stars can be classified by their strong emission lines, For example, if they're carbon rich, they get WC designation. If they're nitrogen rich, they get WN designation. And if they're oxygen rich, they get a WO designation. The system that I'm working on is WR70, which consists of a WC star and an early B-type supergiant companion, which is a fairly uncommon companion type. It is also known that there's variable dust production for the system based on the IR light curve variability. So a little more about that variability. In a 2013 paper by Parader-Williams found that the near-infrared light curves of WR70 show a continuous but variable dust emission. A model of the spectral energy distribution for 1991 gave a dust formation rate of 5.9 times 10 to the negative 7th solar masses per year for the preceding year. And when analyzing the K-band, it was found that there was a maxima of dust emission in 1989.25, and that emission rate was about 1.5 times greater than it was in 1991. Similarly, a minima was found in 2004.7 and had an emission rate 2.9 times lower than what it was in 1991. These maxima and minima suggest a 2.5-year period in that dust emission. So the main goal of my project is to produce the first known orbit for the system, which will help us gain a better understanding of these dust-producing stars. So we received data from the following sites: Casileo archival data that was taken between 1999 and 2012, data from CTIO using Chiron that was taken in 2023 and 2025, data from SOAR that was taken in 2024, data from Gemini South using their GHOST spectrograph in 2024, and lastly from LCO using NRES in 2024 as well. So these plots are examples of the normalized spectra from the various different sites. While the procedure was relatively the same between data from each site, there were differences in the process. For example, for the archival data, I had to go in and reduce every single file that we got in order to make it usable and cut out any hot pixels. While with GHOST, I had to splice together the 35 different orders and cut out any noisy parts at each end of the spectrum. However, where it gets similar is once they were both ready to be normalized, I normalized them, plotted them, and then did a Gaussian fit over the emission lines to find the radial velocity, which were then recorded in an Excel spreadsheet. So those plots are examples of some of the Gaussian fits I did to find the radial velocity, which was found in kilometers per second. We're doing this for 4 different emission lines: the carbon-3 at 4650, helium-2 at 4686, carbon-3 at 5160, and another carbon-3 at 5696. So one of the issues that we ran into when trying to fit over the peak at 4686 is that there's an absorption line in the emission line, as you can see circled in red. Because of this, we had 2 options. We can either do a double Gaussian fit, one over the main emission line and one for the absorption line, or do a bisector method where we take points on both sides of the emission line and fit through there. Although we're still working towards an orbit for the Wolf-Rayet star, we do have a very preliminary orbit for the supergiant companion. This plot currently only has archival and data from Chiron, but in the coming weeks we'll be updating it to include all the data that we have. With this orbit, we also have some orbital parameters to go with it. The ones of most importance are a period of 1,065 days, which matches the previously thought of period of 1,030, and an orbit eccentricity of 0.63, meaning that the orbit is fairly elliptical in shape. So for next steps, while we have the majority of the radial velocities measured, we do need to go back and measure that helium-2 line using either Gaussian or bisector. Additionally, we need to take the measured radial velocities and put together an orbit for the Wolf-Rayet star and update the B supergiant. And lastly, we need to process any remaining data that we have, like LCO in a recent Chiron one. And that picture is my Excel spreadsheet with all the data. Thank you. Any questions?
So how do you pick between doing the double Gaussian and the bisector method?
Whichever one I feel like doing, in all honesty.
Wonderful talk. How do you pick which emission lines you're going to fit? Is it just whichever ones are strongest, or?
So we chose ones that were present in the majority of the spectra. So the 4686 line for helium-2 was present in every single one. And the carbon-3, because it's a WC star, it's carbon-rich, we chose those as an additional one.
Hello everyone, my name is Logan Caudle and I have been working on the last year using stopping cosmic muons to do energy calibration in the CCM detector at Los Alamos. And before I get too far in, I would like to thank the entire CCM collaboration, and specific thanks to Dr. Smith for all of his help on this project, as well as to Darcy Newmark at MIT and Dr. Austin Schneider at both Los Alamos and Texas A&M University. Just a very quick rundown of what the CCM detector is. It is a 10-ton liquid argon scintillator detector that uses 208-inch photomultiplier tubes on the inside, which are these guys right here, as well as 1-inch photomultiplier tubes on the inside the veto region. And these PMTs will then detect light that is produced from particles that stop in the detector. And then just what the detector eventually will be doing is potentially looking for dark matter using a tungsten cube that's right here that is being impacted by 800 MeV protons produced within the accelerator. And those particles that are produced are most likely going to be pions and other particles, which hopefully are a main source of dark matter. But in order to do all this stuff, we first need to calibrate it, and this is where the first part of my project really came into, was actually looking at particles to do the calibration. And I picked cosmic ray muons that stop inside the detector that produce Michel electrons. But in order to actually detect those particles first, I had to actually trigger on them, which is what these things right up here. These are cosmic wash detectors. So there are 6 pairs of them. Each pair looks like this. As you can see, this one was actually taken at Riddle here. And then these will then trigger, giving me a start time for when to look for these particles. And then once these particles are inside the detector, they can stop producing Michel electron following this blue distribution here, with you have the E plus and the nu mu bar. So this is the anti-muon neutrino. And this equation right up here is what gives you this line. And this is really what we're looking for, is this blue curve to get a distribution, because it has a very sharp cutoff at exactly half of the momentum of the muon, 52.5 MeV. So this right here is what my data looks like. Specifically, it is this strong muon pulse here, and then it decays, and then the light decays, and then you get a Michel electron pulse. And this is really what I'm looking at, because I can figure out exactly what the upper bound on this is, and that'll tell me the exact upper limit of my calibration value. But in order to actually get that, first I had to check to see if I actually had Michel electrons, because it's impossible for me to really tell what my particle is immediately. So what I first did is look at the time spacing, this delta t, between the start of this muon peak and the Michel peak. And then I plotted those on this distribution here with this equation right here, using these ratios representing the ratio between mu plus and mu minus, as well as also having a capture and a decay coefficients, these tau cap and tau naught. And the capture is approximately 600 nanoseconds as like the accepted value, so mine's a little on the low side. But the tau naught is roughly around 2.2, which is accepted as the value of the lifetime for muons that decay into Michels. And now that I was confident that I actually had Michels and what I was seeing, the next step was to subtract out this background baseline that was produced from the Michels. And so using this equation, using a Gaussian to start off with to get this peak, and then 2 exponentials, one for the singlet light, which is the short-lived light, and the triplet, which is this long tail here, to subtract out, because if I don't do this, I'm going to have energies that are above 0, which will throw off my calibration. And then once I have subtracted it out, I am left with basically this, which is a nice baseline right around 0, and then just the Michel itself with its own tail. Doing this then, I then integrated over 40 nanoseconds and 90 nanoseconds to just get 2 baselines for how I was going to be doing my integration, which then produced these plots. So this one right here is the 40 nanoseconds, this is the 90 nanoseconds, and unfortunately, as you can see, they don't follow the what we expected nicely. So that was something that we were a little concerned about, and we didn't know what was going on. So the first thing we decided to do really was then look at what caused these big spikes right around 0. There were 3 ideas that we really came up with. The first one was corner clipping muons. The second one was just geometric inefficiencies within the detector. And the one that I've been focusing on more recently is events near the edge of the detector. So this right here is just one run, just so you can have a general idea. So the first thing I did was then found the location of all of the particles in here. And then I basically just cut all particles outside of 0.7 meters from the center of the detector as just like a guess to start with. And almost all of them that were cut out were in this low energy bin right here, which I was very happy to see. Unfortunately, there are still quite a few remaining in that low energy bin. So some of the more work that needs to get done is to just continue looking at what caused those, as well as just finding out the sources, figuring out what other ways to reduce the events, as well as getting better lifetime measurements to actually make sure that we are 100% confident of what we are seeing. Thank you. Questions?
What was the motivation for 0.7 meters to a meter cutting out as opposed to maybe 0.6 or 0.5? Do you think you might find a high grouping of them at those low energies as well if you decrease that radius?
So unfortunately, I was not able to add this on this slide. I did have a distribution of the radial distances, and they were pretty consistent up to about 0.6 or so, and then they started falling off pretty rapidly. I have previously done 0.5, and it started cutting out a lot more in like this region right here. So I was like, okay, I'm going to keep it at 0.7. And actually, recently I found a paper. Actually, Dr. Smith found me a paper from the mini moon experiment that they also had similar issues where they had this big peak, and they also cut it right around 0.7. We have a fairly similar size, and I was like, okay, I'm confident in my 0.7 cut.
Testing. Okay. Hi, folks. I'm Taylor. This is Shannon. And for the last few years, we've been working towards an understanding of the variability and orbit of the massive binary Eta Carina. How do I click? Just do I go like, yes. Okay. We'd like to start by thanking our amazing mentor and his colleagues for their continued guidance, support, and honestly patience, as well as the NASA Space Grant and Embry-Riddle's URI for giving us money. Much appreciated. So Eta is a massive eccentric binary system with a luminous blue variable primary. It's a supernova imposter, so it's already undergone 2 explosions, which in turn created the surrounding homunculus nebula. And this system is well studied and has been studied for a hot second, but it is not well understood because it is super janky. Particularly, it's got an elusive orbit, it's really variable in brightness, and it's got some unconstrained fundamental parameters that we are taking a look at.
Thank you. Okay, so this is where my part of the research kind of comes in. I was looking more so at its orbit. Specifically, what we can do is we can reevaluate the orbital kinematics of the binary star system by looking at the cloud of elements that surround the system. So, for example, hydrogen, helium, nitrogen, all of those fun things. You can pick different ones and you can see how they might outline the orbit in different terms. So with this, one of the big ones is hydrogen, and a previous alumni, Emily Strawn, did work with this with Dr. Richardson, and she particularly looked at the H alpha line and found about 0.81 as the eccentricity, which we will get back to with the end of my research. So first off, just comparing hydrogen versus nitrogen when looking at the star system. So hydrogen is pretty much everywhere in the star. It can be caused from wind collisions, it can be caused from ejecta, it can be caused from pretty much anything. Both the primary and the companion star can eject hydrogen. So there's a lot more data, and it's a lot more broad lines that you can go on ahead and analyze with it. Whereas nitrogen, which is where I came in, the source of it is only the primary star, because the companion star actually doesn't fit the parameters to have the nitrogen develop within the density, the heat, all of that stuff. It doesn't fit it. So we know when we look at nitrogen that it's going to be the primary star. The only kind of caveat to this is that we get what's called a forbidden peak. So this is just something I briefly had to kind of exit out of my data. I think this is the pointer. Yeah. So this giant peak right there, that's the forbidden line. So that would be nitrogen emissions that happen, say, not within the actual wind collisions, but within the actual outside nebula or ejecta that happens from the binary. So that's a pretty important thing, but for my research, we just kind of got to disregard that. So looking in a little bit closer at where we can see nitrogen coming in. I specifically used data from 2025 CTIO 1.5 meter telescope up in Chile. So with that, I took the data and essentially you're given this big data of just raw files. And so once I was able to interpolate that, I cross-correlated it and eventually was able to fit radial profiles against, say, the previous Balmer lines that Emily Strawn had done with her research. And just to kind of show you where my research lies, this plot over here, that is how nitrogen looks, and zoomed in, it looks like there's a lot of emission and absorption. But when you compare it over here, it's really just a baby compared to what helium is. So, and even more so hydrogen if you looked at that. So when we look at this, we really have to narrow in on what we're going to view particularly. So after everything was said and done, I took this data, and right here in this plot, this is as Eta Car approaches periastron. So that peak and the dip in the peak in there is during its periastron event. And so all of this data was me fitting it to the nitrogen emission lines. Now, all of the terms over here, minus the period that has always been fixed within my data and Strawn's data, is pretty important to go on ahead and cross and compare. But the main thing to note when you're looking at this is the eccentricity. So this is where it comes in again from what Emily Strawn was able to do. I particularly took the H beta lines. So H beta shows that they have an eccentricity of 0.91. If you're not familiar with that, the higher to one you get, the more elliptical you get. The lower, the more it looks like a circle. So with something like this, that's already considered highly elliptical. But then from mine, I got 0.94, which means that it's actually probably a lot more elliptical than we had ever thought before. So with that, we're gonna keep on looking at that, and Taylor will go on ahead and talk about her part of the research.
Thanks. Oh, clicking here. Okay. While Shannon focused on the orbit, I was looking into the variable behavior. So Eta Car exhibits these significant periodic peaks in brightness, and we don't know why. They are repeated, they are stable, they've been observed for a long time, but this is atypical for a system like Eta Car, particularly considering that it is a supernova imposter. And so the current working hypothesis is tidally excited oscillations, in which tidal distortions, namely around periastron, can induce variable behavior. Tidally excited oscillations, they've been observed in other systems before, but they are hard to detect, and they've never been seen in a system like Eta Car. So I'm working with 7 years of precision time series photometry from the BRIGHT constellation mission. I have data from 2016 to 2022 with periastron passage. Where's the laser pointer? Let's hope that's right. Nope. Top, this one? Okay, yes, periastron passage here where things go a little bonkers. That's in 2020. So I isolated the frequencies of interest around periastron and calculated their associated amplitudes. But the bulk of what I've been doing has been modeling tidally excited oscillations with the TIDES code. The TIDES code is written in both Fortran and Spanish, which has been a very fun little obstacle for me. But it solves the equations of motion for a 3D grid of volume elements, particularly for a binary system. And so I can simulate tidally excited behavior as a maximum radius as a function of time, and then I can compare those outputs to that of the observed data. I've been really looking at the synchronous rotation parameter, beta naught, which takes the orbital angular velocity as a ratio to the rotational velocity. And so as beta naught approaches 1, the system becomes highly supersynchronized and the tidal forces are highly synchronized, versus for a lower beta naught value, you're going to get more tidal distortion, and that's more likely to induce tidally excited oscillations. So in this top plot here, I have a pretty high beta naught value, and we're seeing this one really intense pulsation, then the system kind of flatlines. Versus for the bottom plot, I have a lower beta naught value where we're getting pulsations that are more indicative of the observed light curve, and thus good evidence that tidally induced behavior is possible. No. Oh boy, what do I do? What happened? Okay. It scared me. Okay, so thus far I've been able to run the tides code for up to 3 orbital cycles at a time, and all reasonable input parameters for eta car indicate a remarkably stable system in which the periastron events seem to repeat almost identically. And so I'm currently working on matching the Fourier amplitude spectrums of the tides output to that of the observed data, and I'm primarily looking to constrain the mass ratio, the eccentricity, and the synchronous rotation parameter. What this looks like in a nutshell: up top, we've got a plot of one of the tides outputs. Then I extract the regions that are in line with the phase ranges from the observed light curve, take a Fourier amplitude spectrum, isolate these frequencies of interest, and compare those values to that from the observed data. Something to keep in mind, I am comparing maximum radius with flux, so there is an intrinsic relationship between the two, but in order to do an exact computational comparison, I would need to know a lot more about the temperature fluctuations that I could ever possibly know. So we're just saying it's going to be off by roughly a factor of 4, and then moving on with our days.
So as far as next steps go, with my end of the research is really to evaluate more of the orbit with an upcoming periastron passage that's actually happening this year, so we can get more data, look at it a little bit more. And then over on Taylor's end, it's to go on ahead and better explore the nature of the system's variable behavior with those tides codes that she's been using, and just between both of us, understand eta car a little bit better, because there is so much fluctuation in what's commonly understood about it, so just knowing variables and all of that a little bit better. And then this summer, finally publishing. Thank you. Questions? Okay. I think that was enough awkward silence.
All right. Hi, everyone. I'm Katie, and I'm going to be presenting on the X-ray insights into colliding wind binaries, a comparative study of WR25, gamma-2 Vel, and related systems. And before I get started, I would like to thank my mentors, Dr. Pragati Pradhan and Dr. Noel Richardson, for their continuous support and mentorship. So before the first supernovae, there are massive stars. These massive stars eject powerful stellar winds that can ionize the interstellar medium and supply and distribute matter to the universe. And so it's really good to understand these systems to see what the first structures of the universe could look like. So sometimes these massive dusty stars, windy stars, are found in binary pairs with each other. And so when they're found in binary pairs, you can see that their winds actually collide into this bow-shaped shock front. And that is something that we can study pretty well. So in this bow-shaped shock front, it actually creates a shocked heated plasma. And so this plasma is described by this equation up here. And you can see that when chi is less than or greater than or equal to 1, it means that the system is adiabatic. It means that we can model it pretty well with some pretty simple temperature models and get a pretty decent understanding of what's going on. However, when chi is much less than 1, it means that the system could be undergoing radiative cooling, which is a much more complex process. And when the winds are actually colliding at a terminal velocity, it gives a constant mass loss rate and a 1/d dependence. So how exactly do we detect these, and how are they cool? So basically, these massive stars, in their stellar winds, basically there's just all these matter that's coming out super fast and colliding with each other and crashing, these energetic charged particles, and this releases X-rays. So then when you have this binary system and this powerful shock front, you have so many more collisions right where that front is. And so this actually creates a powerful X-ray signature that we're able to measure. Some common characteristics of these is a varying flux, because as the stars approach periastron, there's simply more interactions. And then you can also have a varying column density, because there's more absorption as the winds from the shock front are facing the observer. And then the lines, you see more hotter, more energetic lines showing up in your emission, because there's, the winds are colliding at very energetic states. So here is a plot produced from a successful proposal from Mike Corcoran, produced by Tree Fan, one of my mentor's previous students. And so you can see here, this is Gamma 2 Vel, a little wacky system like that we've been looking at. And you can see here that this is following over two different phases. And so you can see that the hardness ratio is changing. It means that as the stars are approaching periastron, things get hotter, things get more energetic, the winds are producing hotter lines. However, the weird thing is that the first cycle and the second are not the same. And that is weird and could indicate that there's clumping in the winds. So why do we look at X-rays? X-rays are really, really cool because they aren't obstructed by all of this gas and dust all around these systems. So it lets us probe all the way up to that shock front itself to really figure out what's going on. And so there's two main ways that we can look at this, either through photometry or spectroscopy. And so you can see the X-ray variation from the separation, just like we saw in the last plot, and the shock temperature over the phase. And so here is a bit of a more of an extreme example. So this is also Gamma 2 Vel, and this was made by Kenji Hamaguchi. And so you can see here that the cool component, which is a little bit far away from that shock, doesn't really get changed by phase. But then this hot region over here also doesn't get changed all that much. But then this middle region is extremely phase dependent. So this is just a bunch of phases plotted over on top of each other. And you can see that the absorption changes quite a bit throughout the phase. And that is quite interesting. And we don't exactly know why that happens. Because if it was simply because, the dust is absorbing, you would expect it to be across the whole way. So here is what I was up to last semester. So I applied a 3T temperature model to Gamma 2 Vel, and then plotted over WR25 and WR133, which are almost entirely the same systems. They're very, very similar with pretty much the same companion and very similar orbits. However, WR133 and WR25 are face-on, while Gamma 2 Vel is edge-on. And so you can see here that it's very similar in the middle region, has much higher absorption. But then you can also see that in the higher energy region, that Gamma 2 Vel actually has more hot emission, which could indicate that there is non-thermal emission in the hotter range. However, we have not found that yet. However, we did see that there is, with Fermi, that there is gamma ray emission, and so it's possible that it's possible that there is non-thermal emission, but it's just in the hotter ranges that we haven't looked at yet. So moving forward, we're going to be looking at more data from periastron and apastron, and just continuing to model these and figure out what's going on. Why is it so weird? Thank you.
Can you remind me of the spectral type of WR25?
The spectral type of WR25.
Yeah. Is it a WNH star? I don't remember. WN, is it with hydrogen or not? Okay, so all three of these have different physical conditions then, because you have a carbon-rich wind for gamma vel, nitrogen-rich for 133, and nitrogen and hydrogen for 25. So that could be some of the differences that we're seeing, and we should probably explore that more. Good talk.
Thank you. Thank you, and that is why you are a collaborator and my mentor. Thank you. All right. Thanks, everyone.
All right. Hi, my name is Michaela, and I am studying the dusty environments around WC binaries with JWST under Dr. Richardson. So, God, this is a horrible place to stand. Jasmine already taught you a little bit about what Wolf-Rayet stars are, so I'm not going to bore you with all those details again, but I do like this cool little diagram here, which gives you a comparison of the size of the Wolf-Rayet stars and their O-star companions in comparison to our dinky little sun. So we imaged 4 of these WC stars using JWST's mid-infrared instrument, and we did it in 3 filter bands, 7.7, 15, and 21 microns. Oh, and sorry, when I say WC, I mean carbon-rich stars. So they are dominant ionized carbon lines that we're seeing in the emission spectra. So we took images of 4 stars in those 3 different filters, and we took 4 dithers of each, which means we moved the camera around a little bit just so we could avoid any hot or damaged pixels. And these are some false color images of each of those stars. And you can see my particular favorite star, WR112, you can see these kind of tree ring-like dust shells. And that is the thing that I care about, is the dust. Because if we're correct and the dust contributes to the galactic dust budget as much as we think it does, that means it was super important in forming stars and planets in the early universe. So what I did is I reduced images using the JWST code itself. So they produced a package that did all of the work for me. All I had to do was plug and chug. Took uncalibrated raw data, and it did a bunch of astronomy stuff to it, like median combining and subtracting off. Sorry, my brain just glitched. It did a lot of astronomy stuff that I'm not going to bore you with. And it spits out a calibrated file, and then I take that calibrated file and I subtract off the point spread function, and then I combine all of the little dithers that I took into a level 3 mosaic image. So, enough yapping. There is the uncalibrated image for WR112. Can you tell which one is my favorite? And when I run it through that pipeline, it spits out this image here. And when I talk about the point spread function, I mean these 6 little spikes here. They're diffraction spikes from the hexagonal shape of JWST's mirrors themselves. And on the 7.7 micron filter specifically, we get this extra artifact, the cruciform, which is highlighted in blue. And on each image, we get a fainter effect just from a support beam that's on the actual instrument, just this little diffraction spike here. So I take these models that JWST so graciously provides for me, and I scale it up, align it with the center of these images, and you can see here these diffraction spikes. They're pretty faint, but they're basically gone on this image after I subtract the PSF off. So that allows us to dig way deeper into the actual dust shells. And when that PSF gets subtracted, I stack them all on top of each other. I make a level 3 mosaic, which I always think these turn out so cool. Made them for all 4 stars. And then I made radial flux plots. So we want to see how far the dust extends into the interstellar medium and how long it survives. So using, again, my favorite star, WR112, I took these cuts coming out from the center of the star, avoiding the center because those are all nan values just from oversaturation of the detector. And I plotted it as a function of radial distance from the star, and each of these peaks is a ring. And so there's 20 or so rings here, and this star has a 20-year period. So that means this dust that we see on this plot has been around for about 400 years. So did that for all of the stars, and some of them are much softer. So like 48A has a much softer curve. These peaks are not as defined just because of its orbit. And then with certain stars like 125, in certain filters, it's just so faint that you can't see anything at all past like 25 pixels. So I mainly work on how far the dust goes from the star, but in the future, because I have done my time and served my sentence and I will be graduating, future students will be working on temperature curves as a function of distance from the star, as well as studying the mass and the density of the dust around each star. And I also, one of the current collaborators, Corey Kell, she's a junior, they're going to be working on shell geometry, so seeing how the shells actually form, because we don't fully know if they're actually concentric rings or if they're a spiral formation yet. So I hope to see those results in the future. And I just want to say a huge thank you to Dr. Richardson, my mentor, because he has been an immense help, not just in capstone and research, but throughout my entire time at Riddle. Genuinely would not be graduating without his help, so thank you. And to my collaborators, Corey, who, as I mentioned, is a junior here, Emma Lieb, a PhD candidate at University of Denver, as well as Ryan Lau and Pereter Williams, who work at Noir Lab and University of Edinburgh, respectively. Thank you.
So do you know, you were talking about like the difference between like some of the shells showed like more spikier like dust shells, but some of them were like softer like in your plots. Do you know why that could be happening?
So if we go back to the plots, so this star, I think 48A has a period of what, like 32 years? I'm trying to find Dr. Richardson. He's nodding, 32 years, which is 12 years longer than this star here. So these rings are going to be more spaced out. And then 48A is, it's weird. It's just weird. The dust that's surrounding it really gets in the way, and I can't dig in to the rings as much. I don't think I have an image of, unless I do. So 48, I know how to read, I swear. So this is what it looks like without those cuts there. So you can see that it's just really faint. It could be a multitude of things. It could be orbit, it could be brightness itself, it could be eccentricity. Yeah, I hope that answers your question.
Thank you.
Hello. Oh, yeah, okay. I know how things work. Alrighty, y'all. I'll be talking about coherent states and coupled supersymmetry. Before I start, I want to see if, okay, that's how the laser pointer works. Okay. And I'd like to thank my mentor, Dr. Williams, for helping me set up this project and making it possible. So, basically, before we can talk about coherent states, we must first talk about the quantum mechanical harmonic oscillator. In non-relativistic quantum mechanics, wave functions, or basically the position of these particles, are defined by the Schrodinger equation right here. Oh, right here. And I like setting all the units to 1 because we're doing math. We're not doing really much physics. We're doing physics, but, you know, whatever. And arguably, the most important system in physics is the spring system or the harmonic oscillator. This allows for really good approximations using second-order Taylor approximations near maxima or minima and potentials. And in quantum mechanics, it has the added benefit of having a really nice algebraic structure which describes the creation and annihilation of particles. So basically, you look over here, and we see that we have some quadratic potential, and these are each of the solutions, where we have some like Gaussian, and then it keeps going, and it keeps oscillating more like that, and higher. So basically, how can we think of the system? We have right here a cat on a ladder. And we have these two operators which happen when we factor the harmonic oscillator. Basically, it's like a difference of squares, like x squared minus a squared is x minus a, x plus a. And basically, using that, we're able to apply the annihilation operator, which brings the cat down the ladder by 1 and solves for that solution. And then the creation operator brings the cat up the ladder by 1. And basically, we're able to solve for every single solution from one solution. Okay, so now what are coherent states? Coherent states are the most classical quantum states. That is like a really good way of thinking about them. They oscillate similar to the classical harmonic oscillator, and they're like Gaussian wave packets that move around. So coherent states alpha have 3 properties in this quantum harmonic oscillator case. It's not necessarily in general, but they're eigenfunctions of the lowering operator. So basically, if you take out a single particle of the system, nothing changes. Subsequently, there is some unitary transformation, d alpha, or d, yeah, the displacement operator, such that when applying it on the ground state, so the bottom solution on the ladder, you can get all of the coherent states. So you can think of that one as like translations or like modulations of the wave function. And finally, they also have the minimum uncertainty state, which is very good if you want to describe like classical behavior, because you don't want things to go like all crazy. Anyways, so instead, we're going to be working on coupled supersymmetry. And supersymmetry is, we have like basically the standard model of particles, but then we can also have their supersymmetric counterparts. And basically, supersymmetry describes moving from one particle system to the other. So like, if you have like a fermionic particle that's like spin 1/2, you can get like the bosons from the other side. And coupled SUSY has this relationship right here, where we have 4 creation and we have 4 operators that describe the coupled ladder structure. But I end up liking to use them in a matrix form because it makes it easier. And very similar to the harmonic oscillator, it has this really nice commutation relation that allows for a ladder structure. So how does this ladder structure work? Like the cat example before on the ladder, instead of the cat going up the ladder, the cat can move and go to the other part of the ladder right here. This is you apply the creation operator. You do it again, the cat will go to that space. And the cat will keep climbing up the ladder, getting every solution. Okay, so now we have all the background. Let's get the results. So we want to see what coherent states properties arise in this case. Do we have the eigenfunction, the lowering operator? If we take off a particle, will we actually get a state? Yes, we do. We get this disgusting equation right here that corresponds to the states on the ladders that we have. And it is defined for every of the complex numbers, so we don't have any issues with that. And it is the most general solution. There's also like other ones if you do for specific cases, but I want to solve it in general. Okay, now let's keep going. So displacement operators, do they exist? Kind of. Yes, like yeah. And there's the formula for it, kind of. So displacement operators is you apply them on the vacuum state, and you get any of the coherent states themselves. The issue is this thing is not unitary, and what that means is it doesn't preserve probability. So if you move it slightly, stuff's whack. So it works for the vacuum states if you, or it works from applying the vacuum states to get the coherent states, but you will have to add a normalization factor. And basically, we can go to the third one. Now we have the uncertainty principle as well. The uncertainty principle doesn't quite work the same, and the reason why is because Robertson's inequality does not necessarily hold. So basically, in quantum mechanics, we have unbounded operators. So they're like momentum and position, the eigenvalues of them go up to infinity, like they can be arbitrarily large. But what ends up happening as a result of that is the domains of these two operators might not be properly defined. So when you apply like AB and then BA, they might not be in the same domain. You might get some weird stuff going on, and you might get functions that actually don't satisfy your boundary conditions. So as a result, Robertson's inequality is out. We can cross that out. We have to use variational principles, and that's something that we're continuing to work on and that I'll be working on over the summer. And we expect coherent states to have a minimum uncertainty for each given x and p, but this will not be constant for each of the like expectation values of the position or momentum. And we'll just have to keep working on that in the future. So, questions? Yes. Oh, I was about to hand you this.
That was wonderful, as expected. You went over some analogous operators for your symmetry. Is there a number operator in your new model?
Yes. Let me get the cat to climb down. Okay. So, because we have this relationship right here, A star A is again just the number operator, and we get a same spectrum, but instead of it applying like, so when you take the number operator and you commute it with A, you get negative A, and then you get this matrix right here. So it's not necessarily like a scalar times the annihilation operator, and similarly with A star, you can apply an A star, and then A star is on the other side. So we have some weird non-commutativity with this matrix right here, which makes a lot of our analysis a lot harder. So yeah. Any other questions? Yes. Sorry.
Sorry, I don't mean to delay. If people need to leave, they can. If this is the last talk?
Yeah, I think so.
Where is the breaking of the symmetry? Where did you do that?
What do you mean breaking of the symmetry? You mean like on this ladder?
Well, I think at some slide you said the
partially
supersymmetry was broken. Or partially.
Yes, I apologize for not talking about that. So basically what partially broken means is that we are only looking at one of these ladders. The red stuff on here, the cat skips the ladder and jumps to the next one. So basically you can have unbroken, partially broken, and completely broken. And the partially broken means that we only worry about one of these ladders because in the case that we're looking at for the Fourier-Bessel, this doesn't satisfy a lot of boundary conditions that we've imposed. So basically, we only have one ladder structure to worry about. So yeah. So all the red stuff are eigenstates that should exist, but we don't have them. Yeah.
On the slide with the standard model, I think it's the previous one. Yeah. Are you saying that the fermions become bosons?
Well,
or is that just an example, like
it's
a flip?
It's an example of supersymmetry, but basically in supersymmetry itself, you have like the fermionic particles right here, like the quarks, and then they're like supersymmetric counterparts. I do believe they're like bosonic type particles. I'm pretty sure that's right. Basically, so you got the up and down quark, they become the sup and stown quark. People are very creative in physics. Yeah, it's wild. So basically, these spinor type particles become bosonic. So it's like, it's interesting. That's not necessarily what we're worrying about in our case. That's something that normal supersymmetry has, though.
Okay, so I thought these were the exact same images. You just flipped them, but I'm just realizing now they're different images.
Yeah, they're different because these ones we haven't actually like determined. People think they exist, but you know that's up to be shown. I don't think so. Whatever. Anyways.
Okay, thank you.
Yeah, no problem. Oh, there's another. Okay. Cool.
I just want to say great talks to all the students, and I think all the professors would appreciate a picture of all of you before you head out today. So thank you again to everyone.
Just a quick announcement. Of course, thank you everyone for the wonderful talk. We have a next series of talk. So we have 10 students there, and the next talk is going to be on April 24th. So see you all there.